So welcome back to Coding Like It's the 1990s. We're still doing assembly language in our own custom processor. And today, I got a couple of announcements. The most useful of which is that, not that one. The most useful announcement here is that I should know what I'm doing first, right? Alright. I need to quit saying alright, don't I? The more useful announcement is that we are up on GitHub. So we've taken all of the Yup 5108 package of software and the emulator and the assembler, and we put all that up on GitHub under a public license so that people can add to our infrastructure of applications and make your own games, that kind of thing. And one of the things we're going to work on today, after we get past all the announcements, is the shell program, or what used to be called the command prompt. And you've seen it we've done a little bit of it before with just single letter commands. But we're going to expand it so that we can do full commands, much like DOS or Linux or any of those other operating systems that have pre-existed. And then I think I've got a good architecture, if you will, to make it to where it's easy to add new commands. So we'll have all the same single letter built-in commands for the ASCII table and test code and things like that. But we'll add we'll put in a method that'll allow you to add your command name, the function pointer to what to do when that command is entered, and the pointer to the help string that explains that command. We're going to put all that in a little table, and then anyone else can just add to that table later on as long as the names don't overlap. And we're going to make that easier by keeping it case sensitive. Yes. One of the four horsemen, the four horsemen of the software apocalypse. Case sensitivity in strings and file names, spaces in strings and file names, which we'll get into why that's a headache. Then big endian, little endian, and there's probably another, I don't know. Anyway, so me and my filler words. Alright, cut that out. So, alright, we're up on GitHub. We'll have the link in the description. We've got a package here. You can either just download the zip file, or if you want to contribute, you go ahead and create a fork off of this repository, and then as you make your changes, we can merge them in with the main line, all that kind of fun stuff. Got my tea with me today. Let's see. Okay. Maybe I should have background music after all, just so I'm not talking to myself so much. Alright, so we've got that and that, and we got that there. Let's see. We're going to create a shell program, and I kind of want to make something of a sort of an icon. So here's what I'm thinking. So the Oreilly, something like that. Not O'Reilly's, but is it Oreilly Computer Books? Yeah, these guys. have a whole series of books, I think. Yeah. Let's see, where's the best place to see this? It's probably looking at images. So here we go. So a bunch of the Oreilly books have various animals on the cover for their I guess mascot. So we've got things like the Git Bat and HTML. What is that thing? Anyway, was that a little bush baby for VI and a snake for Python? A python for Python, maybe? So anyway, I want to have some sort of animal. Let's create some sort of animal mascot for our shell program, just for giggles. AI image generator. Let's just make this full screen behind me. Maybe not. Maybe not so full screen. I don't know. Well, we'll do it for now. And then go over here and move myself out of the way just slightly. What? I hate when things don't behave. Why aren't you letting me move? Alright, well, I'm going invisible for now. Let's just do that. That way I'm not in the way. Alright. So now that I'm not visible no more, I am the ghost in the machine. Let's see, what kind of we want. Oh, there's our puppy pictures on the side, and some what do you call it? The design that I picked up for the background. Let's see, let's make a shell program, shall we? Let's see. A snail. A snail mascot for a shell program for the EUP 5108 microcontroller. Like, it has no idea what that means, but it does know microcontroller. Let's see what it'll give us. 1-to-1. We want it to be something, it might as well be pixel art, right? Since we're all 8-bit. Let's give us 4 options. Alright, well, this doesn't take but a minute or so. Let's see. Oh, sorry. Oh, come on, be faster. Be faster. Ah, there we go. I don't know, what do you think? Which snail should be ours? I like the detail on that one. Should we make him a psychedelic snail? I don't know. Let's try. I don't like that one for sure. That one, there's like a little too many pixels. Let's try this guy. Let's evolve the snail a little more. Let's see what they come up with. So if you haven't seen this tool before, it's FOTOR, F-O-T-O-R. Relatively inexpensive. it kind of competes with Midjourney and the like. Depends on what kind of fanciful things you're trying to create, but I don't know. Which snail to snail? Let's change it up a little bit. A psychedelic snail, a geek snail mascot for a shell program for, let's just call this the CPU. Pixel art, maybe not pixel art, maybe we'll do something more. Let's try logo. It is a logo after all. Let's see what that does. Bet you didn't think we'd be doing some AI art right now, did you? Whoopsie. Okay. These are not right. These are really bad snails, don't you think? I guess that one's kind of close. Let's evolve this one and see what is. It's hilarious when you use a picture and it's expecting a picture of a person and you give it a picture of a dog, and so you end up with just the absolute craziest. Oh, that's not bad. This guy got too many antennae. Yeah. This guy got the geekier glasses. Kind of half and half between these two. What do you think? Any guesses? Snail A, Snail B, Snail the first, Snail the second. I don't know. I kind of like Snail the second. His glasses are too square. They look kind of like a guy, I guess. I don't know how to. Do snails even have sexes? I don't know. Although this one bears a greater resemblance to me, and I can always erase the extra antenna. It just doesn't look much like a snail. Yeah. We'll download them both and figure it out later. We'll do a poll. How's that sound? That snail or that snail? There we go. Well, that's enough fun with the image generator for today. Let's get everything back going. There we are. Back on the scene. Alright, so we did not need this at the moment. So we're talking about a snail this whole time. So we have a new main function, the shell program, and we'll figure out a name for the snail later. But for now, he's Sheldon, because why not? Sheldon the Snail program. So he's going to come up. He's going to boot a banner. And let's make it. Hello, my name is Sheldon. Sheldon. That's probably too many L's, but whatever. Alright. So we just created a new additional string of characters. This is the location we define in this language. We define constants. In this case, the D's define the constants in ROM, or program mode, program memory. And in this case, it is the definition of a string. So every time you create a variable, you create a name, and creating that name is eventually placed somewhere in memory after the program is loaded. In our case, we build everything already located for where we want it in memory. So once everything's assembled, we can look at the symbol file back here, and it will tell you the address of every one of your defined names. We'll zoom in a little bit more here. And we don't need that for this. So in the case of the shell banner, that is going to be in the, let's see, well, unfortunately these are not in any particular order. Oh, that's not going to be in, is it? Oh, that's not going to be in the Bootmon application, is it? It's going to be in the shell. So shell symbols. There we go. Where's our shell symbols? Shell symbol. And down here is somewhere. There we go. Shell prompt. So we create the variable shell prompt, and by using the D, the assembler says, oh, that's going to be this location in ROM, and it is going to consist of this many bytes, whatever 99 minus 96 is, and that shell prompt, let's bring that up here, is this many bytes. So then we have our shell command. Once we assemble this, those addresses should change because we have added to the shell prompt. Let's cruise on over to this folder and build and run it. So we're not running automatically, we're just coming up. So if we hit F5 to run, there we go. My name is Sheldon. Sheldon. And then we have our little shell prompt, and this is where you would, this is where you, I typed in, I can't type as fast as I talk, where you would enter a command, much like the Windows command prompt. And then when you're done, we're going to execute that command. In order to execute a command, we need to know what the command is. And in this format, we're going to assume the first word is the command. And so we needed to strip the first word out of the full line that we typed in order to find out what the command was. Now, there's a function for this in the C language called strtoke to tokenize a string based off of finding spaces. So it would just split the string up into a number of substrings, each with a single word. But we don't need that complexity. All we really need is to copy until we find the first space. And that'll be our first word. And we already have a library function that copies until it sees the first 0 character at the end of the string. That's our string copy command. So in our string lib, we have our string copy. Where is it? That's our string copy constant. Here our string copy function. So this copies a string from one place in memory to another place in memory, and normally runs until it hits a 0, a null character. This is actually the cause of many of security issues in the C language, because the programs were simple and they just ran until they fall in first 0, and if you overwrite that 0, then it just continues off into oblivion and it causes problems. Especially if you're writing into an area that you're writing more bytes than you have set aside, then now you're writing into areas that were not meant for that purpose. And if you're clever enough, you can put in values that are other programs and cause viruses and such to happen. It's called a buffer overflow attack. So here we are. In our string copy command, we're already going and copying until we get to 0. So rather than create a separate function for this, what I created was a separate variable to look for. And that's our string copy delimiter character. So if you want to look for the first word, you set it to a hex 20, which is the space character, and it ends up string copy only copies the first word. If it's set to 0, like it should be normally, then you copy the entire string as normal. But it could also be, say, a comma, if you're looking for different, to split up a string that's separated by commas, or vertical bars, or any other single character delimiter. And it's a bit of a cheat, if you will, because I should really copy the entirety of the string copy function, make another version of it, and so on and so forth, but I save space doing this. And I only have 65K of ROM to run, so you might as well try and save space when you can. So that gives us, this is what the shell program does so far. It takes in a command line, it spits out the first word of that command line, and then it goes back to getting another command line and spitting out the first word of that. Notice I didn't even bother to put the carriage returns. So I keep saying so. Quit saying so. Don't say so. Am I whispering this to myself in my head? Alright. There's Sheldon. Let's get some more inspiration for Sheldon, shall we? There he is. Ain't he cute? Or not that one. That one. No. Is that one? Or that one? Yay! That's the one, right? I can hear some giggles in the next room. So here we go. That's our Sheldon. Here's Mr. Sheldon. Let's see. We have back over here on the up shell. So if we let's take a look at the original test program, the boot monitor. So the original boot monitor, it's like a, I don't know, test code, if you will. So I didn't really comment or pre-design what I was going to do here, or create any kind of architecture. I just, straight line coded it. So here we are in the main, and let's zoom in a little bit. And so what this does is it does the same kind of thing as the shell program. It gets a command string, calls getLine, puts out a carriage return, loads it up, gets the length of it, loads it up again, and grabs the first character, or saves the first character, I should say. Oh, yeah. So that's our string length. So first off, let's break this down line by line, shall we? That is the limit for our command string length, with whatever you want it to be, but that helps make sure that you don't overwrite your available buffer. Makes it a little bit more secure. Then we load up our command string pointer, and we call the function getLine, which reads a line into that command string and does all of the character manipulation for handling a backspace and putting out the cursor and that kind of thing. After we get it, we print a line feed. Then we want a couple other things, so we're going to load up the command string pointer again, give it a call to string length, then load up the pointer to string length variable and store that value. And then we're going to acknowledge that we're finished with the string. Actually, not sure I need that line. So that gave us the string length and the actual whole string. And then here we were loading up the command string and using this to load the first character of the string and making all our decisions based off of that first character, which is doable but less than ideal. It gets you some basic functionality, but you run out of characters very quickly. So, you know, we did this whole process of we load the question mark into the A variable, we subtract A from, or B from A. If there's anything left over, then, in other words, if that subtraction resulted in anything other than 0, either positive leftover or negative, then we want, it was not the question mark. Because if you subtract the question mark, the value for question mark, from a value for question mark, you get 0. So that's where, it being actually 0, we fall through to this line where we call the help function, and then we jump back up and get another line, get another command. But you notice we do this over and over in this function for each of the commands that we have. We have the T command for the test function, we have the M command for the memory function, C for clear string, which doesn't actually run off to a function because clearing the string is just a matter of printing a few things. So we'll find the VT command for clearing the string, screen, print it, command to go into the home cursor position. So in that case, we just do it here. We don't have a separate function. But you can see how this gets kind of unwieldy. It's what in the C world is the equivalent of a switch statement, where we're essentially saying switch on the value in B. So this would be, C version of this was switch B, open bracket. And then down here, through all of these lines, we're essentially saying case question mark. So switch off the B value in case the B value is a question mark. We do these functions, and then this jump back up to the top is something equivalent to the break that you have to put in for every one of your instances of each one of your case values. So this becomes case T, break, etc. So that gets a little unwieldy you can see it's already kind of a pain, and it's only just a few of them. So what I want to do is turn that into a loop and make it to where I can run through a table of values and function pointers of where to call, and also help strings, so that you can, in a standard fashion, do question mark and a command name, and then we can print the help string for that command name. So that's the idea. So to create that table, however, in here, we're creating the table as the shell command map. So the first thing we have is the help command. It's going to consist of you putting in a question mark, and that's the help message. And then this is the actual help message definition: question, command for help on a command. So question produces this message, and then if you said, say, question, whatever other command like memory, then it would print the help message for that command. So that defines those two things: the help message, the help command, and the help function, which is already defined down here. And so we have these three values. Let's see, is that where we want to put it? Probably not. I probably want to put this down here. And then we'll do more of these. And here's our help function. So in main, do screen clearing, we print the prompt, we get the command string. Here's where we're setting the string copy delimiter to a space, and then we load those up and do string copy. And so that will give us our one word. And here's where we print out that one word, but instead of printing it out, we want to run through this table and see if it matches any of the commands in the table. And to make sure we don't go on forever, I'm going to, how do I want to do this? I can just define a string after it. So we're going to basically run through every entry in this table until we hit one where the help command is blank. And that amounts to writing 4 zeros, which we can do with the string command pretty easily. And there's our 4 zeros. Alternatively, we could do it with the literal command, wherein you put in pairs of hex characters. Kind of either way, right? So that'll be our end of our list. So let's see, we're going to need an iterator, a value we can get to while we're looping, and we can either make that a global variable, which is probably bad form, or we can make it a local variable. And to make it a local variable, we all we have to do is say constant main.i is the stack pointer +1, and then decrement the stack pointer so that we have that space for that one character, that one byte. Now, every time we do that, we want to make sure that before we return, which this is main, so we usually note return from main, But yeah, I guess it doesn't matter, does it? We're never going to return from main. We're just going to sit in there forever. But what we are going to do is go back to main.do when we're done with all of our calculations and stuff. So, and that's what that does. Jumped along to main do. So this is the combination of a humongous do while loop. This is essentially, that was the do part. This is while one, effectively forever. So we create our indexer. All right, we got our one word. Now, how do we do our string compare? We want to compare the two strings, and I think I already have that function written. We have string compare constant. Oh, bother. Oh, I do need string compare constant because I'm comparing the variable in memory, which is the first word, to the constant in ROM. So let's see, string compare constant, we have to push the source address and then the destination. All right, so the source address in ROM and the variable address in memory, and then we call it. So much like the string copy function. So, which, let's see. Think here. We should probably have a local variable for the currently working yeah, main.pointer to the not command string, what do I call it? Command map. It's our command mapping tree. And we're going to want to go from one to the next. So, assuming we eventually have, we're just going to put them here commented. So eventually we're going to have like there's the help command, then there would be the ASCII table command, I guess. So and then that will eventually have a whole set. So eventually we're going to have several sets of these 3 lines, one for each of the functions. And I can even make this a separate file so that we would only have to edit that external file to add new commands to our shell. But we'll be lucky if we get this far. If we get far enough to actually execute the help command. But in any case, that's kind of the idea. And actually only need 2 bytes at the bottom. now that I think about it, because these are all 2-byte values. So 6 is the size, right? So that's our shell map. Let's make a constant shell command map. Do we need such long names? Let's just call it command map shell entry size. That's 6. That's the size of 2, 4, 6 to get from one command entry to the next. Alright. We now have our one word. Now what we want to do is we want to, and that's our word, is this is first word entered. And so we're going to put that on the stack here shortly and do a command compare. But first we need to put the entry of the constant from this table help command. We need to put that on the stack. And that is, to begin with, this plus 0 offset. And plus 0 offset, let's all right, I'm back. Let's initialize our iterator by loading 0 into A. So load into A 0. And then we're going to store onto the stack whatever's in the A variable. And that will automatically increment or decrement the stack for me, rather. So that's 0. So eventually we want to do this. We're going to run through the table until we hit a 0. So the first thing we're going to do is check if we're at the last one. Oddly enough, the first thing we do is see if we've gotten to the end. So we're going to define a main dot, we'll call this map search, because that's where we start the map search. And the first thing we do is see if we've gotten through all of the map search items. And we do that by taking let's see, we have the command entry size. So we're going to load that into A. So load into A from the EEPROM or ROM this value. What actually the assembler replaces all of the C's that are defined. It replaces before it does the actual assembly. So that has no overhead. So we're going to load into A this, and the reason I do this is if I put 6 here and then later on the table changes, then I'd have to remember every place I put 6 for the table size. So this way I only change it once in the one place at the top. So we load that in, and that gives us the size, and we want to get POE. It says effectively, this doesn't follow the rest of the naming convention, but it says we want to take the current stack pointer and add to it the offset of this value, which is main.I, And so we just say POE main.i, and what that does is it takes a stack pointer, copies it into the data register, and then adds the 1 to the value, and now we have the data register pointing to our temporary variable I. Load B from memory, which is to load B from whatever location the DR register is pointing to now. That gives us which one we're on. Now we have A and B, so we can call mulBA, which multiplies B times A and puts the result in DR. And then since we're going to be limited to 255 divided by size of entries, so divided by 6. So that's the limit to the number of commands we can use right now using this technique. So now technically 256. So 42 entries. Good enough for now. Right? There's another technique I could use that wouldn't have that problem, but I'm going to do it this way this time. So this is essentially dereferencing an array entry. So if this table up here is the equivalent of a data structure in C, it would be the equivalent of this would be struct command map, right? And then it's a pointer, or in this case, in the C language, it would be a short pointer called help command, and that equals this defined help command value up here. And actually, this really what it should be is, this will just be the command, we'll call it maybe the command word, right? And it's going to be equal to the help command. Let's go ahead and spread this open a little bit more. Oops. Short help. CMD function is the help function. And then this would be right. So that would be one version of an entry. This would be a command map entry. And then since I'm creating an array of these entries, there would be another in memory in the same order, another batch of these command execution function and message pointers, one right after the other in this array. So what we're doing is we're saying this data structure, command map entry, can't have the space. So command map entries, the size of that is this. So this is the equivalent in C of char CMD map entry size of the command map entry, except that there's no actual size of function. I just looked at it. So but giving you an idea, that's roughly what the C equivalent of what we're doing here. Let's close off that structure, shall we? Alright, so this is an array of structures, and as such, we need to know the structure size, and then in order to find the entry, in order to effectively do dereference shell command map. So let's copy that, come back down here, and so this whole exercise here is attempting to dereference the location of the shell map command, or the shell command map entry for each item that we have a command map entry for, based off of the iterator. So we take the iterator, we multiply those two together, that value comes back in dr, but we're really only going to bother with the R part because it's easier than adding two 16-bit values. I suppose I should add two 16-bit values, but anyway, for now, I mean, that's what makes the limitation of 42 entries, but we don't have that many for now, right? And so said so many programmers in the past. We don't need it. Who's gonna need more than 42 commands, right? Stuff like that. But we'll revisit it if we ever get that big. So we multiplied the two values together. Now we have the offset from the shell command. So, well, first off, we need to take that value of R out. So let's load into A the value of R, the value that's in R, and then we're going to load into the DR register our shell command map location, and then we're going to sum into the data register D and A. So we take which one item we're on, we multiply it by the size of each entry, and then we add that to the base location, and that goes down from the top entry down, and that is effectively pointer arithmetic, because that's how arrays work. All right, now let's see, we've got now we should have our pointer to our first entry. And if we look at that pointer, we need to make sure that the next two bytes are something other than 0. So we can load the bytes into B and immediately test. And if it is, then we're done looking through the command map, and we should do this only if we run through the whole map and we get to the end and we don't match a command. So if that's the case, we're going to like print out a little question mark, what in the world, unknown command or something like that. So we get our map, we add those two together. Now we're pointing to the entry, but in theory we're pointing to the last entry. So if we're pointing to the last entry, we need to load B from memory and jump a long distance. If that is not 0, that means either of these bytes is not 0, then it's an actual pointer. Probably the first one's not going to be 0 anyway, but we'll just do this for now. So main dot map found, or command found, or not command found. So the next thing we're gonna do is check for command match. It's gonna be down here somewhere. There we are. All right. Trying to spare you from my coffin. That's not what I wanted to copy. All right. Now between here and there, we well, that one, but now we have to increment the dr pointer to the next byte and check it for 2 as well. So if that's not 0, load the second byte. And if that's not 0, we continue on. And we check for a command match. But if both of these, if we've managed to fall through all of this, neither of the bytes is anything other than 0. And that means that we've reached the bottom of the list and we didn't have a match. So now we want to load up something. How do we want to do it? How do we want our error to be? Something like command not found. And then maybe give it the command. Is that kind of what we want it to look like? Or how does DOS do it? So DOS, if you type in a command that's unknown, it says this long-winded blah is not recognized as an internal external command operator. Really, we just need to say blah blah is not recognized. Or no, I guess we could be more generic and say, let's just say unknown command. It's not recognized as an internal or external command, blah blah blah. Let's just call it unknown. But we can leave the quotes. Right? So you're going to put in something like that, and it's going to come back with not found, unrecognized, How about command you say? I know nothing of this. How about that? No? Whatever. We'll keep it simple. The command unknown. How about that? So, first off, let's define that message, right? There's our help command. So, that's built, not build in. All right, define unknown command, and that is a string where we're going to do the other part manually. So let's just have a space. Unknown command, exclamation maybe, and it did. I don't know. Sometimes you include the new line character in the string itself, and sometimes you leave it out and let the system do it. And we'll let the system do it. So that's our string unknown command. Didn't mean to do that. Copy that. We got down to here, and there's a 0, so let's load up that command. Well, actually, let's load up our one word. We're going to write 1E. Uh-oh. I can probably do that. Then we're going to LDR one word. Print string 1E. Write 1E, end quote. Load up the string unknown command. Let's just put a comment in here so we know what we're doing. Why we are at the end of the table without a match. So we get to the end of the cable, there's no matches, so we're going to print the word in quotes and then say unknown command. And then we're going to give it a line feed, and that's the end of that. We go back up to main do. Oops. Jump long, or jump long for all the time. You know, if we really wanted to make it like C, you would jump down to this line and then this line would jump up there, but it seems redundant. Let's just go ahead and spaghetti the code a little. Alright, so that presumes we ran through and we got to it. Gotten to the 0. Now, if we haven't got the 0, there's some sort of command match, or there's another command to match, right? So let's check for a match. And to check for a match, we need, so this is a bit of a conundrum. So if I jump at this point, the current value of the DR register is still looking at this entry, the beginning of the entry, right? Now, so I could get there and the DR would either D or R would be blank, or would not be blank, but I don't know which one, and I no longer trust the value of the DR register, but I don't want to do this whole calculation again. So instead of doing the jump not 0 here, I am going, we've loaded it into B. I'm going to load it into B. Yes, I'm going to load it into A rather. Then let's just increment, load into B. Then we're going to sum A and B. And if there's anything else out there, of course it won't be 0. The only way to get a 0 is if we sum two zeros. But that means we know where our pointer is. We're pointing at the second byte of the entry. And then we run down here to match. And the first thing we can do is decrement the DR to get back to the first byte of the pointer. I know it seems a little odd, but this way we're not having to do the whole setup and calculation again. So we decrement D, and now we want to put this address on the stack, much like we did for the string copy. So it's scr.scd. So that pushes the R value and then the D value onto the stack. Then we load up the destination, or not destination, but the oh, that's kind of annoying. So if this matches, we're going to have to do the recalculation again. I don't want to do the calculation again. So this is where, oh, I was already doing that. This is where we put the pointer to the command map, and we decrement the stack. So there's our command map pointer. Decrement stack twice. That gives us a space for it. Alright, so that's our command. So after we do our calculation to figure out our command map value, which is right here, before, yeah, let's store it before we're doing anything else with it. So we now have our value in the DR, the offset of the map entry point, and we want to put that in our temporary variable. So we are going to load AR, load BD. So that copies the DR value that we loaded from here and added to into A and B. That gives us space in the DR register to load up the pointer to that variable. Then we can store indirectly the value A, which was the lower register R. Then we can increment the DR register and store indirectly the value B. And now we have it stored off. All right, and conveniently, we still have it in A and B. So if we sum A and B, and we get anything other than 0, then that value is something other than 0. And we have it conveniently stored off, so instead of having to do this decrement, we just need to put that value on the stack. So we'll load that up into DR, and then load into A, store that, increment the DR, load into A, store that again. There we go. So that takes the value that we found of our command map entry and puts it on the stack. Then we put the value of the string that we read on the stack, and we call string compare const, which is probably not named exactly that. Oh, what do you know? It is named exactly that. All right, so the way this works is we're going to look at those two strings, and it's just going to run through until a mismatch is found. Let's see. And then when it returns, basically just runs through until it says there's a difference or not. String compare diff. All right. So, yeah, so subtract A from B. So if there's nothing left in A, so basically if there's a difference, it'll come back and A will be something other than 0. If there isn't a difference, let's see, where is that? If there isn't a distance, it will run through all of this. Yeah, I think that's it. I'm just kind of surprised we didn't have that, but it should. Yeah, I think if they match, A will be 0, and if they don't match, A will be something other than 0 upon return. Although that comment is not here for some reason. Nothing like leaving out the comments, huh? Yeah, I think that's how it'll work out. Because yeah, if I remember right, that was the idea. It's been a while. So I guess we'll see easy enough, right? Since we can single step. So we can call the string compare constant. And I'll patch up the stack from where we were. And then let's just halt here and let's just halt here and see how it goes. Better not to do all so much at once and not do off testing. So much rather test often. So not what I wanted to do. All right. This is a command. Be done through all that. Yep, sure enough, come back out a string copy constant, and A and B are something other than 0. Now this should match question mark. No, A and B are not. Well, let's walk through it. Let's put this up at the top of the map search. Actually, that's print banner. Let's get the string. Here's where we get the one word. So let's stop just before we do the map search. And we'll see how well that's working. All right. So question mark something or another should be a match, right? So we halt. We're loading the command size of 6 into A. And we're going to get the location of main to the I, which should be that, right? Should be 0. So we load that into B. Then we call move BA, which multiplies to 0. Right? So this is why this should work. Then we load 0 into A, and we load the shell map of 1870, add 0 to it, then I'll load this location into A and B, 1870, and get the location of the command map entry, which is these 2 bytes here at the end of RAM. Ooh, I wonder. Well, we're about to see if this confuses things, because we're writing right at the very end of RAM here. No? Okay, good. It didn't overdo it. I was afraid it was going to wrap around to 0. Let's see. Add those together, we get some value, so that means we're not at the end. So we can check the map entry. So here we load command map entry. Right, 7E, load that into A, store that on the stack, then we increment the DR, load that into A, store that on the stack, and we're going to load our value for our word. What? SCR and SCD. Doesn't appear to have worked. Well, I guess it did, we're just not looking at it. Okay. So now we're going to call string compare constant. We got a 59. It's not a null. Let's get the address. So the other location in memory. Load that. That's 3F. Well, one of the convenient things here is I can run up the Bootmon in a separate instance. And oops, wrong button. Run it up. There's our ASCII table. And 3F, sure enough, is the question mark. So we are reading the question mark properly, but it looks like we are not reading from, so we're reading this question mark, but we're not reading the constant correctly. That says there's a difference. We return. So let's see. Command map entry. That should do RD. I don't think these, yeah, those worked. Man, let's see, what's our time limit here? We got a little ways. We'll give it another 10 minutes or so. If you like what you see or you want to see more, Feel free to join us, like, subscribe, put on the bell button, because you never know when we're going to be doing stuff. Be sure to like, give it that thumbs up. Thumbs up. Goofiness. Alright. Let's see. What happened to our match? Well, one way to do this is we've loaded that up. Yes. And before we do this, let's print out what we're looking at. Because the first pointer is the command string. So let's go ahead and load that up. We're going to do this little rigmarole where we load A with wherever that's pointing, which is the R of what we want. Then we're going to increment the pointer. Then we're going to load D with whatever's in memory directly. And then we're going to load R with whatever's in A. So we're just doing a little value shuffling around. But that allows us to do a call to print string 1E. So that should print the command map entry that we're looking at. Then we load it up, stick it on a stack. And let's do the same thing with the word that was entered. So this is essentially calling, let's see, this would be printf and a string, and I don't know why I feel to make it so exact, but in any case, p command map, and this is p command map, and inherently, because it's the first item in the thing, it's the command string, because it's the first item in the list, or the first item in the structure. So that would be the command itself. So that prints it all out. And then that'll print out the word. And I guess in between, let's print out, I don't know. Let's see, vertical bar. What's vertical bar? Vertical bar is, where are you, Mr. Vertical Bar? 7C. So this should print the command map string that we are currently looking at, and the word that we thought we got typed in, and then we're about to compare them. So this makes sure that we're looking at the two items. This is essentially debug printf, if you will. We're going to throw these away, but for now, we want to see what both values come back as. So we should see question mark, vertical bar, and then the first word we typed, which for our test is question mark, right? So let's write a line feed character. So it's pretty. And let's see, that's it. Get out of there. run the shell. So word to, and we get to that line, just run. Ooh, look at that. We seem to be pointing off into oblivion. That is clearly not where we're supposed to be pointing. And is that our vertical bar? I don't even know. It's all sorts of gobble. So clearly we are not looking at the right entry, but we should be looking at the shell command map and the first string for that. No, we're not. We're not looking. We're looking at the pointer to the string to that. So to dereference that pointer, yeah. So we're doing wrong. Command map tree. No, that should still be the same value. Well, let's double check as we go. Reboot. K. S. All right. Command entry size 6. We're on the 0th entry. We load that difference up. 1870. 1870 in wrong. There's our 1870. There's our command map. 1870. There we go, it's 1870 again. And that's 1870 in ROM. No. Yes. Well, kinda. Yeah, I see where I screwed up here. So that needs to be a D. Because the first word we entered is in DRAM, not EEPROM. But the string from the command map is from the EEPROM. So if we call print string 1E here, still printed a bunch of gobbly. So where is that? Where is the thing? 1870. Let's look at symbols. There's one word. So to C. Command shell map 1870. Yep. And 1870 in the map file. So the symbol file breaks down the addresses given to each symbol. And in our case, there's a difference between the ones in ROM, which are all of these things, and the ones in RAM, which are the ones down here. So constants versus variables. And we do a map file that sort of tracks as we assemble where everything is getting located. So to know where everything gets located, let's open up the map file of the shell. Here we go. And so 187E. Help command should be written after it. Help message. So let's look at the ROM itself, shall we? 187E is way down here. 187E. 187E. 0. That's F. 7E. So 1859 and 1886 and 185B. So they are right in values here. 1859 1859 is probably there. I'm going to guess because 3F is a question mark. And there's another 3F. Space, yeah, that's space there, space there. So that is the command. One eight 187E. 1859. This is Little Indian. That's why I'm reading them backwards. So 1859, 185. Certainly 3F00. That's our string for a question mark. So that is pointing in the right direction. But what I should be reading out is 1859 is the one I'm looking for. So let's reset. Alright. So we can get this all set up. Right. Our 187E. So we want to get want to load right now. We have 1870 there, but what we want to load is that dereferenced yet again. Yes. So essentially do all of this one more time. Complicated dereferencing scheme we have going on here. Not really, but shell program, get it running again. Run. Load up that value. Then we load up that value. And we have some sort of entry. So that loads up 1870. Then from that, I can't do it from memory. Yeah, so the first time I did this, it was reading it off of the stack. That was from memory. Now I want to read that location out of Flash. So I use F for Flash, E for EEPROM, a couple of different references. Just there we go. That should give us the value we're looking for. Run out of that there. Oops. Sum it up. Alright. We load our 1870. That's our base location. We read it from a temporary location in RAM, but this is a location in ROM. So now we load a increment. What? Oh, LDF. Yeah, there we go. So 1859 is our pointer to our string, right? Let's run and find out. Yes, there we go. Question mark, vertical bar, I don't know. That's there we go. So that gives us the string we're looking for. That's why we weren't comparing properly. So we do all of that to get the string we're looking for. We don't need to do this anymore, nor do we need to do any of that. And instead, we load a from Flash. Then we're going to store from the stack A, increment, then we're going to load into A from Flash again, store A again, so that should, instead of setting it up to print, is now putting the values on the stack like we should. Now we should compare to one word, and let's see what we get now. Mismatching. There we go, certainly mismatching. question. B is 0. So that's probably the match, is when B is 0. I know we don't have a second item yet, but that should technically be the easy part. So, alright. Well, I think we're coming up on our time right now. Want to save a little evening for the cooking and eating part of the evening. So thank you very much for joining us. Join us again next time. Like I said, make sure to ring the bell for notifications, because we come and go at will. Nothing like an inconsistent schedule, eh? Well, jobs changing around, things are moving. I never know when I can get online for any length of time. So hopefully next time you see me, we'll have the rest of this worked out, and we'll be processing commands and adding commands and that kind of thing. And until then, thanks for joining me. We'll see you next time. Bye. Bye.